tell you what the layers of the atmosphere are. So one of the things I want you to be familiar with is in the Earth's atmosphere, which is that kind of tenuous little envelope of gas that's gravitationally held to the Earth, we have oxygen. Remember we said that actually in our air, I think it must have been on Friday, we talked about our air is like 80% nitrogen. And we talked in here, the symbol for nitrogen is N, and actually it's a diatomic element, so it's 80% N2 and about 20% regular oxygen, okay? So regular oxygen actually has 2 oxygen atoms that are stuck together. Now ozone, you probably heard of ozone. Ozone actually has 3 oxygens stuck together, okay? So the formula for ozone is O3. So now there is good ozone and bad ozone, and I don't know if anybody would buy this, but my thing, and the good ozone protects people on the Earth. So my thing is we take some of the bad ozone, which is bad for people, which is here in the low layer of the atmosphere, and we pump it up to the higher layer. Okay, so the good ozone actually is in the stratosphere. So remember where the stratosphere is. It goes troposphere, stratosphere, mesosphere, thermosphere. So the stratosphere is right above the thermosphere. And the good ozone actually helps us so we don't get cancer. So they're not really exactly sure, how to prevent cancer, but they do know that ultraviolet radiation, we talked about the cousins, UV radiation, which is just a little bit shorter than visible, wavelength, a little more intense. Actually, that particular wavelength from the sun can cause cancer. So that's why we do these UV blocks and everything when we go out. So the thing about it is if we screw up our good ozone, if we screw up our good O3 in the stratosphere, then we lose that layer of protection, okay? And chlorofluorocarbons, CFCs. Now you guys are young enough, you probably have mostly remembered that we don't have CFCs actively. We used to have CFCs in our hairspray, okay? Just basically as a propellant. We used to use CFCs in our coolants as a coolant, okay? And that's not, it's kind of cool because the whole world kind of came together and said, look, these are screwing up our O3s in the stratosphere. We cannot have CFCs, and so they kind of came together and made that happen. So that's good ozone in the stratosphere. Now bad ozone, and I went ahead and brought in this little picture from the internet. If you've ever been driving down I-80 or in the St. Louis area, you may have seen these caution signs, and they are ozone alerts. Now that actually is bad ozone that's created by pollution. It's just what we call kind of a secondary pollutant. So bad ozone is if you have asthma, it can really give you a hard time. So bad ozone is just a human-made thing in this layer, in the troposphere. So see how I just say you take some bad ozone and pump it up to the stratosphere. No one's ever taken me up on that, but if you ever hear it come to fruition, you'll be like, Mrs. Snipes talked about that. So then I have a few slides here. You probably heard about the hole in the ozone layer. So that must be a hole in the good ozone, right? Okay, and it is. But it's seasonal, and it's actually just limited to the poles, okay? So the hole in the ozone layer, and I kind of talk you through, it's a little story. How do you get the hole in the ozone layer? How is it seasonal? We talked about 10 cloud types, but one cloud type that didn't make it because it's kind of a unique cloud type is actually polar stratospheric clouds. Polar stratospheric clouds. And polar stratospheric clouds occur in the poles. Not so surprising. It's really cold there to create that upper level cloud. Most clouds are in the troposphere. Most weather is in the troposphere. These are in the stratosphere, these special clouds. Okay? So here's the deal. What they do in the springtime is basically they start to go from being a cloud, nice cold winter. In the springtime, they start to the cloud melts. I know the cloud doesn't melt. But basically the cloud goes from being probably solid ice particles right to being a gas because it's springtime. Okay? And so what happens then is there's a bunch of O3 that was trapped in those clouds, And as those clouds break up in the springtime, then they go ahead, and when the ultraviolet radiation from the sun comes in, okay, there's O3 here that basically, CFCs here, I said O3. There's CFCs here that have been released. They actually screw up your O3, and so you don't have the protection in springtime. So what you're looking at here, they're Dobson units, I believe. This is actually looking at the Earth kind of this way, okay, and this way, okay, because that's where you get your ozone hole, okay. So the more blue it is, I believe that's like indicating kind of a deficient in O3 because the CFCs have been released because the clouds have been evaporating. Okay, so that's kind of how that works, the ozone hole. So this is a nice figure that actually kind of shows you the layers of the Earth's atmosphere again. Okay, so when I draw, in my drawings oftentimes I'll kind of draw the Earth's surface like this. Okay, so that's the Earth's surface down here. And you kind of get a sense for how deep they are, because the scale along the y-axis actually is distance above the Earth's surface. So here we have, 10 miles is about the troposphere's stops, 30 miles, okay, mesosphere up to 50 miles, the thermosphere up to 200 miles. Okay, so that's kind of the way the Earth is structured. Now there's an important aspect also on this figure. Can you kind of see it kind of waves back and forth? The reason that it's waving back and forth, this graph, is because of the temperature. So along the, I guess it got cut off. Drat. Oh, another technical thing. Along the, this axis, along the x-axis actually is temperature. So if I could clear my slide here, I'll draw in some temperatures. Oh, boy, goodness. I'm guessing maybe, let's keep it in the Celsius scale. This might be 30, okay, 20, 10, 0, okay, -10. Now, I'm not sure that what those are, but I'm just guessing. 40, 50, 60, and this is all degrees Celsius, okay? So what this is saying is that as you go up, and actually it's right here, over here. Let's start with the troposphere, okay? Can you see where as you go up in the troposphere, okay, as you go up in the troposphere, it gets cooler. And that makes sense. Remember, Earth going up, does it get cooler when you climb a mountain? Yeah. But I'm here to tell you that when you switch gears from this layer, and if you were to climb Mount Everest, for instance, you'd still be in the troposphere. And I looked it up. I'm like, really? Yeah. Okay. So, but when you leave the troposphere, as you go up in elevation, check this out. It gets warmer. Okay. This is where it's getting warmer. Okay. And as you go up in the mesosphere, then again, you're getting cooler. You're right here. And as you go up in the thermosphere, you're getting warmer again. Okay, so that's kind of what that snake thing is kind of trying to show you. But most of the weather actually, like I said, occurs here in the troposphere. Cool. Well, this is why I brought some props here today, to kind of talk about air pressure. And in your physical science book, I think clear back when they talked about states of matter in the physics unit, they talked about kind of gas laws and gas pressure. So if you kind of want to liken today's lecture, that's probably how you need to kind of go back in your book. Okay? But one of the things about matter is that if matter is a gas, it is, and I think we talked about this recently when I talked about water. Okay? That if matter is a gas, it actually has a lot of kinetic energy. The cool thing about gases is that you turn them loose and they will, what we say, they will fill the room. They'll bounce all the way around this room if you have one little gas particle. Part of the reason it wants to bounce so much is it has a lot of kinetic energy, okay? And basically the other thing is it's not connected to anything. I think we talked about intermolecular bonds. Okay, so we are focusing on water vapor. I want to talk about, again, I guess not just water vapor, but just, I guess, gas particles in the air, not just water vapor. So this could be a sample of this room, okay? Sample of the air. These little particles are gas particles. You kind of get a sense of that. I don't know if you can look, but they're showing like little wispy motion. Okay, these things are banging around in this room, okay? Let's look at what they are. Well, they're showing the green ones are nitrogen, N2. The red ones are oxygen, O2. And every once in a while, because in lab on Thursday, you guys came up with how much water vapor there was in the room, okay? So every once in a while, these are, you see these water molecules, okay? So one of the cool things about gases is that they all work together. So they kind of have a collective sort of situation going on. So all of the gases in here, whether the nitrogen, oxygen, or water vapor, are all kind of creating a pressure. They're creating a pressure what we call independently and kind of collectively. Okay, so you may have, if you're gassing up tires, either your bike tire or your tire for your car, you're probably going to, put gas in it, air it up until it has a certain PSI. So PSI stands for pounds per square inch. Okay, so that's a way of saying how much pressure you have in there. And then, like, if you have one of those little tire pressure gauges, it looks like a pen, you just stick it on there and it makes this thing fly out to the certain amount of pressure that's in your tire. Okay. Yeah. So, like I said, all of the gas particles in a common place kind of work together. So all the gas particles in this room are working together. All right. So how do we say, so we're going to use a tire gauge to get the gas pressure in your tire. So how are we going to get the gas pressure of our atmosphere? Which I'm going to try to convince you what that pressure is in our atmosphere is actually very important with regard to weather. What is your pressure? So if you've ever looked on the Weather Channel or something like that, they will tell you what is your pressure, okay? And usually they will tell you it in inches, what is your pressure, your atmospheric pressure. Now when they tell you it in inches, what they are doing is actually using this sort of thing called a liquid mercury barometer. So, of course, mercury is an element, and it's one of the few elements on the Earth that actually is a liquid in its liquid state. So this is how they get the inches of pressure. Your meteorologists get the inches of pressure. Basically, they have an open pan of liquid mercury down here. This is liquid Hg, okay, down here in this pan. And they count on all the gas particles where that measuring device is to basically hit on that pan of open mercury. And then as a result, what will happen is this mercury will climb up this tube. This tube is closed at the top, and basically a vacuum has been drawn. So the more the pressure, the higher it climbs, and the more the inches of mercury that are reported. But usually more than that, when we look at weather maps, what they have done is they have used maybe a different type of device, and they report pressure in terms of MB stands for millibars. That's how meteorologists usually report pressure. Okay. So, vapor pressure. So that's why I brought these things. So here's the deal. Let's see. Let me get a little bit of lights here. I'm not sure what lab we're going to do Thursday, but I'll come up with something. I thought about doing this one, but I think I'll kind of just show you. Now, here's one thing. So let's just say you take a confined, or take a chunk of air that you have confined, okay, and you heat that chunk of air up. Okay, those air particles are going to go faster and faster and faster. Okay, so as they go faster and faster and faster, they're going to create more pressure. So this actually, my first little thing here to do is to basically take this whole thing and I'm going to put it in the hot water. I think I'll turn that down a little bit. Okay? And my area of interest is right here. Okay? You guys know, and you guys might have used these bottles, but when I squeeze it, oh gosh, when I squeeze it, it's got an issue up here. Okay, when I squeeze it, it comes out. Okay? When I squeeze it, I basically create pressure and it comes out. But I can create pressure. I can increase the pressure of that air just by increasing the temperature, the kinetic energy. And there she goes. Okay. Another thing, kind of like that, is if you've ever bought in a balloon and let's say it's kind of wintertime and you buy a balloon and you leave it in your car and you come back and the balloon looks kind of shriveled up. Okay, it's kind of underinflated. What's happened is no gas is left. Basically, that gas has cooled down. Okay, and it's it just doesn't have as much pressure as it used to have. Okay. Here's another one for you. This one. Okay, so the gas of interest now in this little thing is going to be, this is close to the top, and I'm going to put this in the water. Okay. The gas of interest when I put this in the water is basically, water's going to be here and the gas of interest is going to be trapped here. Okay. So again, I'm going to heat that up, okay, and the pressure is going to increase and it's basically going to, see if it bubbles out at the bottom. It might be hard for you to tell these bubbles versus these bubbles. Let's see if we can tell. So again, I'm heating up that air. Those air particles have more energy. They have higher pressure and they're basically plopping out the end. Okay? Higher pressure. Well, another really common way to increase your pressure is so I apologize in advance. Sometimes these things get a little carried away. Is this, where basically my space of interest is my balloon. Right now there's not really much gas particles in there. I can use this to basically increase gas particles. Okay, so if I go from 0 gas particles to more gas particles to more gas particles, okay, I'm increasing the pressure inside that balloon. Gas particles. More gas particles. More gas particles. More gas particles. More gas particles. And I can do this to kind of get a sense for kind of that pressure of that gas. Oh, let's just do this. Okay, because I've done it before, and I'm like, oh my gosh, there's something. Oh, no, nothing at all. Okay. Okay, so that's increasing pressure, decreasing pressure. I do have another one. Okay, so this one, these are Alka-Seltzer tablets. Plop, plop, fizz, fizz, right? Okay, so that fizz is gas. That fizz is carbon dioxide. So the cool thing about these is they're just kind of, I don't think it's too complicated in chemistry, but there is a chemical reaction going on creating carbon dioxide. So we'll put a couple of these into here. This will be our space of interest. Okay. And this is kind of like when I blew up the balloon, I was increasing the number of gas particles. So basically, right now, when I start out, there's not a lot of gas particles in here. Not a lot of gas particles. Okay. I'm going to add water. I'm going to create the fizzing. Okay. And then the gas particles are going to increase. Okay. The first thing, while there's room, actually what's going to happen is those gas particles are going to make that bag bigger. Okay? But when it runs out of room, okay, they're just basically going to jack up the pressure. Okay? So this actually is my containment chamber, right? Yeah. Okay. So all we need, the other ingredient to make our carbon dioxide is just water. Okay, so fizz, fizz, seal, seal. Okay. So as there's room, the number of gas particles increase, and if there's room, it's increasing the volume of the container. Okay. Now it's kind of running out of room, and I have a certain pressure here. Okay, I can kind of feel the pressure. Okay, but it's still creating gas. But there's only a limited amount of space it can expand to. Okay, it's really tight. If I had a little pressure gauge, it'd be going, it'd be like needling over. It's like nice and shiny. See a little bit of water. Yeah, that might be about it. Okay. No boom there either. We were a quiet sort of Monday. Should we squeeze it? No. That wasn't too bad. So if you increase gas particles, you increase pressure. If you increase temperature, you increase pressure. If you cool down, you decrease pressure. Okay? So pressure is important. Pressure is important. So one of the things with regard to pressure is we have this thing with elevation. Okay? Elevation means kind of how close to the Earth's surface or how upwards you are. So these little particles are trying to show you gas particles. So next to the Earth, the gas particles are closer together, and as you climb a mountain, the air gets thinner, and that's kind of, to me, what this is showing you. The air is getting thinner as you go up. Okay, the pressure decreases. So this is showing you the same thing. Pressure decreases as you go up. Now, this is pretty cool because it actually has... okay. So the way you read this is we have pressure down here, pressure in terms of millibars. Now, at the Earth's surface, the pressure is usually about 1,013 millibars. That's just a general rule. That's a nice, steady baseline. Pressure can be greater than that, pressure can be less than that, but 1,013 millibars is about it. So notice then, as you go up in elevation, your pressure decreases. So we could take anywhere, we could go like here at 12 kilometers, we could say that that's a pressure of about 200 millibars. That's how that works. Right. So we have I'm going to go ahead and in the next part, we're going to look again at our, remember we looked at weather maps? We drew in weather fronts on weather maps. We're going to look at weather maps again. And on weather maps, you've probably seen them, I think, let's see, I don't know if they're color-coded, but actually you've seen an H before. H stands for high pressure, okay, and I'm going to put an L up here, low pressure. So we have a high pressure down here. As we go up, the pressure gets less. Anytime you change anything, in this case pressure, okay, pressure goes from high to low, we call that a gradient. In this case, it's a pressure gradient. In biology, we have our cells respond to different gradients of like salts and things like that. A different concentration of salt outside the cell versus inside the cell. Different concentration, that's a gradient. Okay, so this is a pressure gradient difference. Okay, specifically, and we're going to talk horizontal here in a minute, but do we all buy this, that this is vertical pressure gradient? Okay, So that's just in general the way pressure goes. So let's take a look at, actually I printed these out because he was like, oh my gosh, I have to write all that down. So I have a couple of questions from your textbook, or I have a couple of short answer questions in your textbook, and then I have a couple of just questions. Okay, so these will be due on Wednesday. So we'll go ahead and kind of look at, is this for me? Yes, it is. See, thank you. Go ahead and look at the next part. If we can. Oh, technology has not been my friend today. There we go. Okay. Okay, so we talked about pressure. So vertical pressure is like this. You know, we have down here in the troposphere, we have the greatest. Oh, by the way, your homework. One of the questions I said, I not only want how does the pressure change as you go up in our atmosphere, but also how does the density of the air change. So I hope we're okay with the air is more dense here and it's less dense as you go up. Okay, that was one of my questions to you. The pressure, where you have the greater density of air, kind of like the little experiments we looked at, the greater density of air means higher pressure. So that was a vertical change. Now let's talk about horizontal differences. Now you're like, well, how would you, and horizontal differences are basically, if I'm here in Iowa, okay, there's a difference in pressure over here, and I might be going the wrong way, but, or I'll go down Missouri, okay? So we have a different pressure here in Missouri versus Iowa, okay? How does that happen? And actually there's 3 different ways that can happen. One way is basically, we talked about air masses, right? Basically, a chunk of air can sit where it's cold and become cold and then move on. A chunk of air can sit where it's warm and become warm and then move on. That's one way that actually 2 locations, horizontal locations, can have a difference in pressure. In general, warm air is fluffier. In general, warm air, it has a lower pressure. Okay? Cold air in general has a higher pressure. Okay, so that's one way you can get pressure difference. Another way is your chunk of air dry or is your chunk of air moist? And again, when we talked about air masses, we already talked about you can have these maritime air masses that are moist. You can have these continental air masses that are dry. If you have 2 chunks of air, one's moist, one's dry, you automatically kind of already have a pressure difference. I'm going to try to tell you why do you care if you have a pressure difference between these 2 chunks of air. In general, and this is kind of counterintuitive. When I say counterintuitive, I mean it's like sounds backwards from the way it really is. You might say, oh my gosh, the air is so humid out there. Okay, I just know that's a high pressure. And as it turns out, moist air actually has a lower pressure. That's the way it's backwards. Moist or humid air generally has a low pressure. And since we covered the chemistry unit, I'm just going to kind of briefly bring up these, how much do these atoms weigh, or how much do these molecules weigh? An N2 molecule, if we look at the periodic table, the decimal number for one nitrogen is 14.01. So 2 times that is 28.02. So that's how much an N2 molecule weighs, okay? Oxygen, 1 weighs 16.00, 2 weighs 32.00. A water molecule, you take how much those 2 hydrogens weigh, you add it to how much an oxygen weighs, and you only get 18.02. Okay, so that's to say that actually water is the lightest of all of them. Okay, so actually moist air is generally low pressure. All right. One other way, and this doesn't happen as much around here. Well, I guess, oh, it kind of happens more than we might think, kind of going. But This is where I like to say, if you were to have a bag of candy and go out on a recess, okay, where little kids are playing recess, and you were to throw that up in the air, all your kids would basically come to where the candy is, like a piñata sort of thing, you know. That actually is what we call convergence or converging air. Okay, if you have, this is your candy right here. You put your purple. Okay, if you have candy here, basically everybody's coming in. If everybody's coming in, if you were to look at the density of students, you'd say, oh my gosh, there's a lot of students in one little spot. And kids really kind of freak me out, little kids that aren't my own. So I'd be all freaked out. So actually that is a high pressure. So that is a high pressure convergence zone. Okay. Now, because a lot of people there at once. Now, the other thing is if you were to, now how do I put this delicately? You could either, like pass gas or something, I don't know. But if you were to have something stinky, okay, like a stink bomb, forget passing gas. If you were to actually just do the chemistry and create something that smelled bad, a bomb, okay, you start it there and people would like leave from that area, okay, that's divergence, okay, and if people left from that area, okay, then actually the density in that center of the region where people are leaving is going to be low. Low density, low pressure. Okay, that's how that kind of works. Low density, low pressure. And that happens in weather, okay, or in air, in our atmosphere. Again, we're just kind of talking horizontally, though. Okay, so actually I did bring my version of what's on the slide here today. So you guys may have one of these in your home, geeks that you are, or I just think old people like to know what the weather's doing. Now, the way this works, if you have one, is you see the black dial, right? Okay, the black dial is live. So actually, if I squeeze this a little bit, you see the black, okay? If I just squeeze it, the thing goes up a little bit. That's live. I think this has been squeezed one too many times. This is called an aneroid barometer, okay, because basically it's in contrast to that mercury barometer. Can you imagine people carrying around open pans of liquid mercury? You're like, we learned you're not supposed to play with liquid mercury. That's why all those thermometers now, they're not silvery, they're filled with like an alcohol thing. So that's live, and this little thing is meant to move around. This little silver thing. So what you do is we put it on what the black thing is, okay? Then we come back, I don't know, a few hours later or the next day, and we look to see if the tendency was to increase pressure, okay? Now, in general, if your pressure is rising, in general, you can expect clear skies, in general, if your pressure is rising. And that's why actually over here in kind of the ice, at the high pressure, they have actually fair, very dry, high pressure. Okay. In general, if your pressure is falling, okay, you can expect some sort of precipitation. Now let's think about, what does that mean if pressure is falling? Well, in terms of L's and H's, that means actually I have an L coming in. My pressure is falling. My pressure is falling. Okay, I have an L on the way. If your pressure is steady, okay, so if I were to come back and this black thing hasn't moved from my silver thing or my gold thing that I put there, okay, if it's about the steady, you're like, oh, whatever conditions you have there are going to persist. Okay, so high barometric pressures, and actually I'll go ahead and tell you that if you see a big old H on a weather map, that goes along with this too. A big old H usually brings clear skies, a high pressure. If you see an L on the weather map coming this way, okay, you can think maybe you might see some sort of precipitation, okay? All right. So here's a weather map. It's got a kind of, every weather map is featured for what they're trying to kind of exploit or emphasize. But here you see the H and the L, kind of like I've been talking about. H is a high pressure. If we were to look at that center, that would actually be very dense with regard to air. air particles. This is a low pressure, okay, kind of sparse. Now, let's pick on the low, because lows tend to have kind of that tight bullseye. Can you see the bullseye around the low? Okay, so here's the low. It definitely has the bullseye sort of thing. Let's see what else I have. I'll just put this whole slide up here. That bullseye around a low, each one of those black lines around that L are actually marking locations that have the same barometric pressure, the same pressure. Remember I said that meteorologists like to use millibars instead of inches of mercury or inches? So what they're saying, and it might be kind of hard for you to read, but the lines, or there's actually a number on each one of those those circles. So this is 996, this is 1000, this is 1004, this is 1008, 1012, 1016. If you did the little subtraction, it's actually increasing by a unit of 4 millibars for each one, okay? Those are what we call contour lines. And contour lines are great. You may have run into contour lines if you have ever had anything mapped with regard to topography. Okay, contour lines can tell you what sort of mountains you have or valleys. And in this case, they're marking locations with the same barometric pressure. So put another way is if you were to step from this L out this way, you would be getting higher and higher pressure. Okay, and the reverse is true up here. With these contour lines, if you were to step from this high out this way, you would be getting lower and lower pressures. You can kind of convince yourself if you look at the contour lines. So, can you see how this L has very what I call tight isobars? They're really really close spacing. Okay. That means that you don't have to, they're pretty tight, you don't have to go very far to get a 4 millibar change. You don't have to go very far to go ahead and get that drastic change. Okay? And actually the other one, you have to go a little ways farther. Around the high, the bullseye, the contour lines are not as far apart. Or are more far apart, I'm sorry. Contour lines are more far apart. Well, I want to get to this slide, and then we'll kind of mull this over again when we meet. This has all been building to this idea. Who cares about a high pressure? Who cares about a low pressure? We do. If you care about windy days or not windy days, you care about highs and low pressures. Because honestly, the only reason all wind is basically air relocating from A to B, because A is at a high pressure and B is at a low pressure. That's all wind is. Okay. I have some examples here. So if I were to just take this bulb, we use this to suck up liquids. It's a pipette bulb. But if I were to squeeze it, I create a high pressure in there, and my little gas particles come out. Gas particles come out. What is that? That's wind. Okay? That is wind. Okay? So, thank you. So, it's always from high to low pressure. I feel like one of those people that are selling perfume. So these arrows are wind, okay? Notice that we have a high pressure on the left and a low pressure on the right. So of course the direction of wind is from left to right. The other thing though is the stronger the difference, the steeper the difference in pressure, because these are kind of close together, okay, the greater the wind. Okay, so that's why if you're looking at a weather map that have drawn those isobars, what we call isobars, showing you the different pressures, okay, if they're nice and tight, you're like, oh, that cannot be good for wind. That totally cannot be good for wind. Okay. So like I said, I just kind of wanted to get that far. I'll let you fill in the blank here, but we're definitely going to start on this slide on Wednesday then. And there's no other assignment.